Last time we have discussed some basics in ergodic theory, and today we will continue our journey in this area of mathematics, and we will slowly move to our main goal, what is the limit theorems for dynamical systems. So I recall that now we are working in the setting of measured space, so we have some space with measure mu and sigma algebra B. So mu of x is equal to 1. Our measure is probabilistic, and also we have T that conserves this measure. So this means that for any A from B, measure of A equals to measure of its preimage. And we have proven the following theorem. That if f, the function f belongs to, say, L1 of x mu, then its ergodic averages, so Sn of f, which is just the average of f along the first n points of our orbit, so this is this sum, this converges almost everywhere and in L1 to some function f bar of x, and so there are several other statements here. So this is a Birkhoff or Birkhoff-Hintgen ergodic theory. So let me start with the following definition. Probably I have a bit discussed it last time, but today we'll discuss it in greater detail. So what can be said about this function f bar? So f bar, so we have said that if we consider the sigma algebra of all invariant sets, so this all such A, that the set A is invariant or maybe almost invariant, then f bar is a conditional expectation of f with respect to this I, the sigma algebra. And the most nice case is when this sigma algebra is trivial. So definition, f t is called ergodic if G if every invariant set mu of A either equals 0 or equals 1. Well, of course, every set of measure 0 belongs to this sigma algebra, and its complement also belongs to the sigma algebra. And if there is nothing else, then the measure is called ergodic. So sometimes you say that T is called ergodic with respect to mu, or the measure mu is called ergodic with respect to T. Well, of course, this notation is something that you apply to the pair of measure and the transformation. Okay, so if our corollary, if T is ergodic, then f bar is constant almost everywhere. And if it is constant almost everywhere, then you know what is this constant, because you know that the integral of f bar d mu equals to the integral of f d mu. You see that this constant is just the average, the space average of our function f is an integral over all x of f d mu almost everywhere. And so we see that so for almost every x s and f of x converges, say almost to just the average of our function. So this is what our ergodic theorem says in this setting. So this is, of course, quite nice situation, because then you can say that you have a convergence to some constant, and then, for example, you can study the rate of convergence, or to study this difference between this the sequence and the limit constant, and so on. So this is in fact the main situation to study due to the following reasons. So well, so let us consider, for example, some nice space X, metric, separable. So, for example, you can think about it as a yes, I guess complete measure space is enough for our setting, but you can also ask for more. For example, that it is some manifold or some domain in Rn or whatever. So then we can consider X with a Borel sigma algebra, and we can consider a T from X to X, for example, continuous. Then you can study, you can ask the question about all Borel invariant measures. Or you can say that you can ask the same questions about the general measurable situation, because in fact the fact that T is measurable depends not on the measure, but only on sigma algebra. So, for example, you can say that you have some space X, you have some sigma algebra B, and then T is measurable. This is, again, means that for any A, B, T minus 1 of A also belongs to B. And then you can consider the set of all measures. Well, let's say probabilistic, the set of all T invariant probability measures. Well, of course, when I say measure, I always say that it is sigma additive. Okay, so this is a set of all invariant measures. And ergodic measures, this set has some structure. For example, if we have some, say, if mu1, mu2 belongs to mu, and theta is some point on a unit interval, then theta mu1 plus 1 minus theta mu2 is also belongs to M. Well, so if you take the convex combination of two measures, or n measures, it doesn't matter, then you are still in M. So it is a convex set. for a convex set, it is natural to consider so-called extreme points. So M is convex. So the extreme points, so mu is extreme if and only, well, is not extreme by definition if mu is can be presented as a linear combination of two points. So, for example, if you have some, well, let's consider, for example, this convex set, and then, for example, this point is not extreme because you can say that it is just a convex combination of these points. And this point is also not extreme because you can do this. But for example, this point is extreme because you cannot, so however you choose this segment, one of its ends doesn't belong to our set. Of course, the set here is this, so it's with its interior. Okay, so here the set of extreme points is this curve. And theorem says that mu is ergodic if and only if mu is extreme point of M. In fact, so one half of this is quite simple. If you have not ergodic measure, so if say mu is not ergodic, then you can, so we have mu of A equals, well, belongs to 0, 1, and then you can consider conditional measures. So you can say, so mu1 is just the measure of some set y is a measure of its intersection with A divided by the measure of A, and mu2 is the same for the complement. And then you can see that mu is mu A times mu1 plus well, 1 minus mu A by times mu2. This is not this half of sum. The coefficients are different, but if you think a bit, you can from this formula make two such summands. This is not too difficult, and so therefore you say that this measure is also not an extreme point. The converse is a bit more difficult. You need to somehow explain why an extreme point is ergodic, but this can be done. Okay.
Sorry, I have a question.
Yes.
When we say that measure is ergodic, we mean that it is ergodic with respect to fixed map T, yes?
Yes, yes, yes. The map T is here fixed, of course.
Mm-hmm.
So when we have, in fact, here is the question. So theorem. There is at most one ergodic measure. proof. Well, take any function. You can, or for example, you can take f such that it is an indicator set for some for some measurable a. Then you know that SNF converges almost everywhere to the well, to mu1. So suppose there is 2. And then I want to say that they are the same. So Sn of f almost surely converges to some number. But then you can find out this number because you have this almost sure convergence. So of course there is some bad set when the convergence is something different, or maybe no convergence at all. But from this, but from observing the general point, I can find this number. But on the other hand, this also converges to mu2 of a. Then this means that mu1 of a equals mu2 of a for any a. Hence, mu1 equals to mu2, and that's it. So the question is where my proof is incorrect, where I lied. Any ideas?
So our sequence Sn of f converges almost surely to a constant, which equals integral of.
Yes, so the integral of f d mu1 is equals to mu1 of a, because you have this.
Okay. Mm-hmm.
Hmm? So in fact, the question is the answer is quite easy, because this convergence is mu almost surely. So here it is mu1 almost everywhere, and here it is mu2 almost everywhere.
Mm.
And so there is no problem. In fact, what we have proven is the following: that so now let's write a real theorem. If mu1 and mu2 are ergodic, well, let's well, this is a set of all mu ergodic. Then mu1 is and mu2 are mutually singular. This means that there exists some a such that mu1 of a equals 1 and mu2 of a equals 0. So you can say that the measure mu1 lives on this a, while mu2 lives on its complement. So there is a set such that the one measure lives, so for one measure the measure of this set is 0, and for another measure, the measure of its complement is 0. For example, this is true here. So, for example, here you have that mu1 is mutually singular with respect to mu2. Well, because one lives on A and another on A, the complement. So, and the proof is the following. So the proof is the following. Take A in B, well, if they are different, of course. So we say mu1 is not equal to mu2. So take a set that differs, so such that its measure is different. And then you just define f to be the indicator function of this set A. And then you have this Sn of f goes mu1 almost everywhere to this number, and mu2 almost everywhere to this number, and these are different. So, for example, you can now say that if you take, let's say, C is the set of all x such that Snf of x goes to mu1 of A, then mu1 of C equals 1, because we know that this convergence takes place mu1 almost surely, and mu1 of the complement is larger than mu2 of the set of all x such that the convergence is to mu2 of A, which is 1. And therefore, this is also 1. Yes, because our measure is probabilistic. And so here is this set that that shows that measure that the subparts of the measure mu1 and mu2 are mutually can be chosen mutually disjoint. Okay, so let us now study some examples. And the first example was already discussed on the previous lecture. So we consider the rotation of a circle, and so our alpha we have I have sketched I have presented last time the sketch of the proof that so theorem of the following theorem, that our alpha is has only one invariant measure. Which is Lebesgue measure. And for if alpha is rational. For irrational rotation of a circle has only one invariant measure. And so definition, if M, well, MT So the set of invariant measure of some transformation T contains of only one measure. T is called uniquely ergodic. By the way, the Russian notation here is a bit different. По-русски это называют строго эргодичной. Вот тут есть такое различие в терминологии. So, of course, this unique measure is ergodic by our theorem on extreme points, because if you have the set of one point, then this point is extreme. But in fact, you can prove it independently. And what is more interesting is the following. So in our situation, when our map is topological or even metric space, and we can consider, for example, continuous bounded continuous functions. So the theorem, if x mu is metric, well, if x is metric compact, metric well, compact metric space, and mu is T is continuous, and B is Borel, then if so let's if T is uniquely ergodic, then for any f for any continuous function, its average Sn f is uniformly tends to f bar, which is just an integral of f d mu. So the tendance is uniform, and I don't want to present the complete proof. It is not too difficult, and an idea is the following. It is more or less parallel to what we have done before when we show that every continuous map of some compact metric space has an invariant measure. If you recall that proof, it says the following. So take any continuous function and then consider any limit point of this thing. So you consider a subsequence along which you have some limit. Then you take another function and do the same, and so on. And here you started with one point, with just one point, and so you just take the thinner and thinner subsequences of natural numbers. So, and finally, when you take a diagonal, you have convergence for a dense, countable dense set of continuous functions, and so we have a limit which is corresponds to some invariant measure, and this limit. And here you use Ries's theorem that any nice functional on the set of continuous function correspond to a measure, and you see that this measure is invariant. Here you do the same, but you can say that in the opposite way. So if you have no uniform convergence, then you can choose this, well, how to say, these potential measures in a different ways. So you start, for example, you have some function and you have no uniform convergence. Well, you can take one point x and you can go to some limit as n goes to infinity, and you can, for example, take subsequence such that this stuff converges to some number. In fact, to this number, to the integral, because for most points it converges even without taking a subsequence. Okay, but you can do a bit something more tricky. You choose some sequence of points and some sequence of times that goes to infinity, such that Sn k of f of xk converges to some different number, to some number a, which is not f1, which is not the average of f1. And then you, then you take some subsequence of this nk, well, and xk. So we have now this double sequence, and then you again make some very thin subsequence such that there is convergence everywhere. And again, this functional corresponds to some measure, and this measure is invariant, and so on. So this is more or less the proof. And as I have said, for the circular rotation, we have unique ergodicity, so we have this uniform convergence. And the question is, what is the speed? What is the rate of this convergence? Well, the idea is, so this question can be studied in great details, and it was studied very, very thoroughly. But the first steps are quite simple. So let's start with the following function. Which is just the one element in the Fourier series of such a function. So you take some function and you decompose it into Fourier series, and then these functions are the Fourier basis. Okay, and so if you take Snfm of some point x, well, this is what? This is a sum. Of fm of x plus k alpha, and so this when you write down all these exponents, you have the common multiplier, this one, and then you have just the sum of geometric progression. So you have e to the 2 pi I m alpha to the power of k, and so you have let's see, f of x so here is the sum. First of all, the denominator is non-zero because this m alpha is never an integer. So because our alpha is irrational, this m alpha cannot be an integer, so we have no zero in the denominator. On the other hand, so as for the numerator, we can say that it is something that does not exceed 2. So this does not exceed 2, and this is so we can see that this is you can manage it somehow. So for example, you see that for every such function fm, you have this uniform convergence, because so this function is just multiplied by some number that does not exceed 2, but then you divide it by n and also by some another constant, by this one. But this 1 over n tends to 0, and so everything else is not important. So here. So you see this uniform convergence for one element of Fourier series, and for the general Fourier series. So if you have f of x, which is the sum of some, let's see, g of x is gm times fm of x. You can do more or less the same trick. You say that, well, this is not exactly, well, you know that for the continuous functions, the Fourier series can not uniform. It is possible that it is not does not converge uniformly to your function g. But nevertheless, so the real proof is a bit more tricky. So the real, if you want to prove again the theorem above for the circular rotation, you need one more trick. So you apply, you say that every function fm, every function g, which is continuous, can be approximated by the trigonometric polynomial. This is a Stone-Weierstrass theorem, or maybe in this setting it's just Weierstrass theorem. And so you take this approximation. For the approximation, you have uniform convergence, and the difference. So we have this g minus sum. This is a trigonometric polynomial, and this norm, the continuous, the C norm, the uniform norm, doesn't exceed epsilon. But if two functions differs by no more than epsilon, then for their ergodic averages you have the same. So you see that you have this uniform convergence plus something that does not exceed epsilon. So you wait for sufficiently large n so that that uniform convergence for g tilde. So take n not such that for any n larger than not the norm of Sn of g tilde minus g tilde bar is less than epsilon, and then you have that g is 2 epsilon or maybe 3 epsilon close to g bar. This is an idea, but I want to stress that here that you have some not to, so there is no explicit estimate for the rate of convergence in this proof, because it just says that you can take this approximation, this trigonometric polynomial, but no direct way to measure it. Well, nevertheless, if you look a bit more careful to this formula, you see the following. So as I have said, so let's send g of x is just the sum of all this. You take this g m So here is the Fourier series for the ergodic average. And as I have said, this is estimated by 2. And so if you want, for example, to study the convergence of this series, you want that this thing converges. So if this is less than infinity, so of course you take the absolute values here, then everything is okay. Because then you say that there exists, so you have a convergence, and the rate of convergence is 1 over n. Then SNG minus G bar by in C norm is estimated by 1 over n. A very fast convergence. Well, maybe some constant. Let's look a bit more carefully on this condition. Well, what can be said about the Fourier coefficients of a function? Well, of course, if the function is something just continuous, not too much. You know that there goes to 0, but nothing more. And this is obviously not enough. But suppose that your function is sufficiently smooth. Then what can be said about the Fourier coefficients of a smooth function?
So they converge to 0 as n tends to infinity.
Well, this is even for continuous function, but for a smooth function, you can do the same trick. You can say, okay, so the Fourier coefficients for the corresponding derivative also tends to 0. But the Fourier coefficients for the derivative are the Fourier coefficients for our function multiplied by something like I mu to the power of r, where r is the number of derivatives. So you can say that if f is belongs to some CR, then you can say that GM is estimated by something like 1 over m to the r. Well, and of course, for example, if r is at least 2, then the series converge nicely. But the problem is the following, that we divide this number by something, and the number, this denominator, can be very small. And if it is small, then our series will take some large elements, large summands, and so it can diverge. This is the so-called small denominators problem. It is not a problem in the sense that, in the mathematical sense, it is a problem in more real life sense that you have to do something with this. And in fact, we can see the following, that if alpha is Diaphantine and f belongs to CR with sufficiently large R, large R, then here you have convergence. Okay, so what is Diaphantine? The Diaphantine means that alpha is Diaphantine if for some there exists some d such that for any p over q belongs to q, the difference alpha minus p over q is less than is larger than 1 over q to the power d. This is the definition. So you say it informally. Alpha is Diaphantine if it cannot be approximated by a rational number too good. So in fact, one can prove that every number can be approximated with such that this difference is, well, this is trivial. You just take any q and then arranging, so taking appropriate p, you have this. This is trivial. This is trivial, but one can also prove this, that if you choose p and q smartly, then you have this infinitely many times for some c which is known. So well, c equals to 10 is enough, is definitely enough. Well, but maybe it is your number alpha cannot be approximated much better. And in fact, this is in some sense natural situation. So for example, almost all numbers on the line, almost all with respect to, say, Lebesgue measure, are Diaphantine. And so for this, in this Diaphantine case, you have this convergence, and you have convergence, you have very fast convergence to the limit, to the to this constant. So as you have seen, the rate of convergence is 1 over n. Okay, I think I would stop with this system here, and we will see that this is too much to have the sort of convergence I want to discuss. Because in fact, what we have done here is the following. So the rate of convergence of 1 over n is something very, very strange. It is almost on the something that, so 1 over n is more or less the best you can expect. Why? So 1 over n. Well, of course, there can be the stupid case if you start with an invariant function and then you average it for as many steps as you want, and you have this the same function. So the rate of convergence is that all your differences are just 0. But on the other hand, this 1 over n convergence is so the next best. So let's consider the following function: h, which is the difference of such sort. Then what you have? Then you have that Sn h of x is something like this. And you see that in general, well, of course, so if you choose x somehow, somewhat randomly, then this difference is usually not small. It's at least sometimes it is it may be quite large. So you just take point x and point Tn of x. It is of the order of 1. It is something. So if these points are not closed, we cannot guarantee that f at these points are more or less is somehow small. And so if this difference in brackets is of the order of 1, then the whole thing is of the order of 1 over n. And of course, if you can take f as smooth as you want, and then h is also as smooth as you want, assuming that t is again sufficiently smooth. So there are always some functions such that the rate of convergence is at least 1 over n. So and we see that for a Diaphantine circular rotation, we have exactly this situation for sufficiently smooth functions. And in fact, one can even show that any sufficiently smooth function can be decomposed in such a way. So if for a circular rotation H is sufficiently smooth, then you can decompose it like this. So you can find this F. So this our computation above is quite natural. Okay, but you can see that not too much can be said about these differences when you write it as this. Okay, my second example is something completely opposite to what we have studied before. This example is the following. So our set is sigma 2 is just the bi-infinite sequences of zeros and ones. This set can be, well, it can be endowed with some metric. I don't want, well, let's, so the metric between two sequences is 2 to the minus m, where m is minimal absolute value of k such that xk doesn't equal to yk. So you just look at the closest to the origin element that is not such that they are different, and then you have this. You just take 2 to the power minus m, where m is this distance to 0, and this is a nice metric space, compact, and so on. And you can consider the map sigma, which is just the shift to the left. You take a sequence and then you shift it by one position. So at the new position number 0, you have the term that was previously at the position number 1. So this is a left shift. This is obviously a homeomorphism of this space, and you can again consider the Borel sigma algebra corresponding to this metric. Then sigma is measurable, and we can study some invariant measures of this sigma. And we can define the measure mu p called Bernoulli measures. And I guess this is quite obvious from the name what it is. So if you want to measure the set of all such sequences such that some xi1 equals to some alpha 1 and so this is a so-called cylinder set. You just say something about what it is at the position I1, the position I2, and so-called the position IK. You just fix these positions, and then you say that the measure of this set is, so you take some number p, and you take a p to the power of the number of alpha j equals to 1, and 1 minus p is a number of alpha j equals 0. So, for example, if you consider the measure of all sequences such that at the position 3 you have 0, and at the position 5 and 7 you have 1, then this is p squared to 1 minus p. to the first power. That's it. And the probabilistic interpretation is also clear. You can just consider each xk as a flipping of the coin, and then the results of this flipping are independent, and the result equal to 1 has a probability p. So it is exactly the Bernoulli scheme from the our usual probability course. Okay, well, first of all, what is well, let us assume now. So the lemma is that mu p is ergodic for every p. Okay, let us now believe in this lemma for some time. I'll then for any p here. And what can then be said? So now let us apply an ergodic theorem to this mu p. What will we have? So we take some function f, which is well, of course, you can consider the function on the depending on the whole sequence, but let us consider the function that depends only on one position, the position number 0 in our sequence. So f of x is some phi of x naught. Well, so it is some number phi naught if x naught equals to 0, and phi 1 if x naught equals to 1. And then what is an ergodic average of some function? Of this function, what is this? Well, this is just phi 1, well, 1 over n, by the number of all of x naught to xn minus 1 equal to 1 plus f naught phi naught times the number of all these guys that are equal to 0. So you just take the first element, the elements of x from the position 0 to the position n minus 1, count how many zeros and how many ones are in this segment, and just multiply it to the numbers phi naught and phi 1, and divide by n. So what do we know? We know that almost surely, almost everywhere, Sn phi of x converges almost everywhere to p phi 1 plus 1 minus p phi naught. And this is, in fact, the simplest case of the low-Flash numbers. Well, even strong low-Flash numbers. In quite a simple situation, you have just a sequence of Bernoulli. So you have just a Bernoulli scheme. On each step, you take not an arbitrary random variable, but just 0, 1 with some probabilities. And then you see that you have this convergence to exactly the usual limit. In fact, you can perform what I have said to the more general situation. So you can take, so you start with some x, b, u. So psi is measurable. And then you take the sequence omega, which is a product, the direct product of these spaces. It is more or less the same, but now you say that if you restrict somehow and then you have measure nu here and u on the set of all such that xi1 belongs to some a1, k belongs to some ak, this is mu of A1 times mu of A key. Exactly the same as before. And then for this measure, you again consider the function of x, which is psi of x naught. And then you have just a general case of the strong law of large numbers. So this is a dynamical interpretation of this law of large numbers. And you can also discuss the next approximation. You know, so the law of large numbers says that you have almost sure convergence to some constant. And then you can say, well, what can be said about the difference? You know that the convergence to the difference is not, it's just an distribution. You know that this difference, if scaled properly, converge in distribution to some law, to the normal distribution with some sigma, with some variance. And this is so let us explain how to express the same in our dynamical way, in this mix between dynamics and probability. CLT in these terms. Well, again, let's consider. So this is not CLT, but in fact Moivre Laplace. So we are still in our Bernoulli scheme setting. Well, you just take SNF of x. Well, let's say that our function f belongs to, well, it is normal to say that it has a variance, so in L2, and let us assume that it does not, it is well, if you want to consider this setting, then you can say that psi is here. So this not means that the integral of psi d mu equals 0. So the average value of psi equals 0. Then we don't need to subtract anything from our averages. And then our central limit theorem says that this converges to some to this where sigma square is just the variance of so this is a statement. By the way, so what can be said about the left-hand side? What is the distribution here? Well, you can say that so that on the left-hand side you have some sequence of random variables. So let's write it as eta n. Eta n is a function from omega to R. Or maybe to C, it doesn't matter. And so the key idea here is that you say that this x is distributed accordingly to nu. So this direct product. So in our this x is just the, so again, so f of x is psi of x naught, and so x is just this direct product. So it is its distribution is just so is such that all components are independent and each of them has a distribution mu. this may seem a bit weird, but we can do it like this. And you see that if you rewrite this, then you can say that this is f of x plus f of tx, or in our case, t equals to sigma, right? Plus f of t n minus 1x, and you divide it by the square root of n, and then this converges in distribution to this normal normal law. So this is the natural idea. So the convergence is something that you can observe at the when you normalize the sum by 1 over square root of n, and this is somewhat natural situation. Okay, so this was the very standard example, but it was an example of the system that stems from, from something very special. You just take some direct products, and then you take special measure on it, and then you take you see that, and then so it is somehow the retelling the well-known result of for some special case of action of a measure preserving map on some measured space. But what I want to discuss is can we prove or maybe just state some results for more general cases. And in fact, that's, yes, this can be done, and I will discuss it today and the next 2 times. But today I want to start with another result. Well, okay, so just before I pass to this second step, I want to discuss a bit this statement. That Bernoulli measure is ergodic. I guess this would be one of the problems for our course. It's quite easy, but let me explain how one can prove this. In fact, μp is even more than ergodic. Well, μp is mixing. Mixing means the following: that for any sets A and B, if you consider the measure of the intersection of one set and nth preimage of another, then this tends to mu of A, mu of B. Well, you know that if you just take mu t to minus n of B, then due to invariance, this is just equal to mu of B. But here you consider this intersection. This is as n tends to infinity. So why it is mixing? So the idea, so the impression behind this definition is the following. So you have, for example, some bucket of, say, white paint, and then you just put a little drop of, say, black paint here. So it is just a small spot somewhere. And then you start to mix it. If you do this, if you have ever done this, then you know that this it is this black spot will somehow stretch to something very thin, something like this, And then when you wait sufficiently long, you have just something averagely gray. And this is exactly what is written here. So you start with some B, which is the set of our what was painted black. And also you have, so this is B. And also you take some A, which is a set that we observe. And then you apply your map. So B is somehow squished throughout our phase space, throughout our X. And so its image is something like this. So this is, well, pre-image is like this. And you say that the amount of this image inside A is proportional to the area of A. Well, this is exactly what we, well, it should be proportional in the limit, of course, to this A. So this is the first step. Try to prove that if for some measure you have mixing, then you have ergodicity. And the second step is to prove mixing, but this can be done as follows. Every set, every measurable set can be approximated by a cylinder, by a set of, or by union of cylinders, by a set of this form. And if you approximate, well, maybe a union of finitely many of them, so that the symmetric difference of the rest is small, has a small measure. And then you just have to prove that mixing for such A and B. But if you have two cylinders, A and B, and then you move one, you take N sufficiently large, then the set of, well, when you take pre-image of a cylinder, then you just shift this ij's by 1. Yes, so figure out in which direction. And then you just need to show that, so, and if you wait sufficiently long, then the conditions for A and the conditions for pre-image of B are lie on the different segments of real line. So A says something about, say, position number 0, 5, 22. While if for B you have something that says about the positions, for B you have, say, positions 5, 22, and 26. But when you shift it by quite many positions, say by 100 positions or more, then you have something that deals with only the position of the order 100 and beyond. So, and then you have independence. This is quite easy to see from the formula. And that's it. Okay, so this is the hint to one of the problems to this part of the course. And let us proceed to our next example. Our next example is Markov chains. I guess I don't need to explain what it is. Maybe just specify notation, and that's it. So we have some set A. In our case, it is finite set. This set of states, or also it is called an alphabet. Well, then we have there are two options. Well, let's start with so-called topological Markov chain. For topological Markov chain, you have some matrix M is, well, let's say this is n, well, not n, let's say it's D, is D by D matrix of zeros and ones. You can also think about this as a graph. So we take the graph gamma, so that each vertex is an element of A of our set of states, and you draw an arrow from A to B. This means if and only if MAB equals to 1. So we have some directed graph here, something like this. And this is a topology. Well, what is a topological Markov chain then? Now let's consider the set omega of all sequences X belongs. So just all by infinite sequence in our set, such that well, mxi plus 1 equals 1 for any I in Z. In other words, you say that your X is an infinite path along the arrows in this graph. So that you want, if you was in some vertex xi, the next step you add vertex xi plus 1, and so you need to require that there is an arrow from xi to xi plus 1. Other way to say the same is that this is a set of bi-infinite words such that every two adjacent letters are not from the list of prohibited two-letter words. So the prohibited words are exactly those such that m of AB equals 0, then AB is prohibited. Okay, maybe I want to require that the following, that for any A there exists. So I want to state that from any vertex there is an arrow. So for any X there exists B such that MAB equals 1, and for any A that exists B such that MBA equals 1. This means that if you are at some vertex, then you always have something to go to on the next step, and on the next, and on the next. And also I can reconstruct it backwards. So for example, if I have some finite path, then I can add some infinite paths to the future and to the past, and so we have some element of omega. This is purely technical, because without these conditions, it is not too interesting to study. Okay, well, the next, so this set omega is a closed subspace of just A to the Z. I have already defined, well, I have defined the topology and matrix at 0, 1 to the Z, but here it is the same topology. Well, and so it is compact, and hence omega is compact. And so we are, and of course, the map sigma maps omega into itself. So we are again in this situation of the measure of the smooth of a homeomorphism of a compact set. So this is on the one hand. So this is just some topological system, but again, we can ask now the question: what are the invariant measures of this set of this map? And in fact, there are many of them, but we can construct one particular kind of them. Just let's say metric Markov chain. This is the following. We just now take the matrix P, which is pi ij, with the usual properties such that all pi ij's are non-negative and the sum of pi ij over j equals 1. This is a transition probability matrix. And again, ij here belongs to our set of states. Yes, set of states. Then for such a matrix, we can now if I want to consider this omega, I can do the following. So take our omega m and assume that if Mij equals 0 implies Pij equals 0. So we can do this in both directions. One way, we consider a topological Markov chain. Then we choose any transitional probability matrix such that if at some position at Mij we have 0, then we have 0 even in this transitional probability matrix. Another way, we can consider just a Markov chain, so we have some transitional probability matrix, and then we can just construct the corresponding Mij in such a way that if Pij is positive, we should have Mij equals 1, and where Pij equals 0, we can choose Mij to be 1 or 0 as we want. For example, we can say that Mij is 0 if Pij is 0. So this is two-way correlation of these two constructions. So assuming this, well, if we have a transitional probability matrix, we can also have some P star, which is a vector. This is the vector of P star I, such that sum over I P star I Pij equals to P star J. This is a stationary distribution. And then for stationary distribution, we can now consider the measure mu, well, P star. And now I want to consider not all cylinders, but even just forms where we require something on the set of adjacent indices. So xi equals some a naught, well, x Here is a definition. One can prove that this definition is, first of all, it is that this we have no, so to say, contradictions in this set of definitions. So, for example, if you have a cylinder and then you split it into some other cylinders, for example, you can add requirement on xk plus l plus 1 in any in all ways, and then you just sum over all these possibilities for I l plus 1, then you have the same value, and so on. And also you can prove that this is stationary. So this is an invariant, this is a shift invariant measure. So you have some measure on the set of some u p star is an invariant on our omega m. This is again just the definition, and this is this measure is called Markov measure because it is exactly what we know about Markov chains. So the future and the past are independent given the fixed present. So this is an invariant measure. Again, we need some quite trivial conditions on this measure because there are some exotic cases. For example, we can consider a measure that goes like this. So you have two states and you have with just probability 1 that at each step you go to the next state. There are even worse case. For example, consider this probability matrix. These transitional probabilities. This is, in fact, quite an interesting example. So let's consider two states, A and B, and this situation. Well, first of all, what is A? So AM. So M corresponds to this graph of two. Well, in fact, our requirement forbade this. Yes, because we cannot. If we are here, then we cannot go. But okay, let's do this. What is AM for this M? No, I'm sorry, omega M. Well, omega M is then the set of what? The set of that contains of the sequence that is identically A, the sequence that is everywhere B, and some sort of transitions. So we have xn equals A for n is less or equal to n naught, and B for n is n naught plus 1, and so on. So here are the sequences. So it's just countably many points. Well, let's write down some probabilities for this M. Well, because from B we can go on to B. Here we should have 1, the probability 1, and here we can write down whatever we want. Let us assume that this arrow has no negative probability on it, so we have some. Well, let's say Q here and 1 minus Q here. And then if you consider this matrix pi, you see that, for example, the probability of this sequence is 0, because the probability that you have quite a long sequence of A's, say, is 1 minus Q to the power of the length of this sequence, minus 1. So the probability here is 0, and by the same reason, each of these sequences is also has probability equal to 0. and this sequence has probability equal to 1. So from this point of view, this is from the metric point of view, from the measure point of view. The situation is quite easy. You have just your measure is just a delta measure at one point, and that's it. So we assume that assumption from any I and j, there exists a path from I to j. So from any state we can go to any other state. Then this p star I is positive for any I. So then the probability to be in any vertex, in any particular vertex, is positive. Okay. Now I want to study the ergodic theory of this system. And again, because the system is very close to probability theory, we can retell all this in terms of the usual probability theory. And in fact, we have a theorem central limit theorem for Markov chains. And it states exactly as was already done. So let me so we have assumption 1, we have assumption 1 plus, and we have some function f that well, we can say that f is just a set of fi where I as a state. So to any state we have some value, and our every state with some value of our function, and then we can consider again, we can consider SNF of x, which is just, well, we can consider these random variables. And then this eta n converge in distribution to some normal normal law. And for for sigma square, we can find a formula. Maybe I'll do it in the future when we'll discuss the proof. But now I want to say that this is, of course, not just the variance of this function f. It is something a bit more delicate. Okay, so is again, we should say that here you can think that x is chosen randomly with respect to our Markov measure on our set, on our space omega. And then we have this set of random variables. We have law of each of these variables. And then we have this convergence in distribution. So this is a theorem. But the question is still quite, seems to be quite distant from the systems that are somewhat real. So the systems that are continuous, smooth, something like this. this is just something symbolic. Of course, it's a completely different world. But in fact, this was a huge discovery in 1960s. It was that these two words, the words of the world of this symbolic dynamics, for example, Markov dynamics, and the world of some part of the world of smooth dynamics are very similar. And so now I want to stop our this completely ergodic part here, and I want to discuss a very well-known example that shows that, in fact, this central limit theorem for Markov chains can tell us something about the real smooth map on something on some manifold. Okay, so this example is called, well, it has many names. Well, one of the names used in Wikipedia is Arnold-Katz map, or maybe Arnold-Katz. Well, it was invented independently by Arnold, Tom, and many others. So well, let's not stick to name here. Okay, and for anyone in the field, it's known as just 2111 because of the following. So consider a two-dimensional torus, and consider a matrix. For example, we can take this matrix. What is important about this matrix? It is that this matrix belongs to GL to Z. Well, what is GL to Z? GL to Z is the set of 2x2 matrices with integer coefficients, and what's more, what should also we require? Well, what is GL to R? We have 2x2 real matrix such that what?
So non-zero determinant. Yes,
but here is a slightly so a difference that is negligible in the real case, but important in the case of Z. The difference is the following: GL2 of R is a set of all invertible matrices. This is an equivalent to what you have said, but for GL2Z we have the same. It is the set of invertible matrices such that the inverse is also a matrix with integer coefficients.
So we okay.
Okay, so A is the set of, well, let me write it down. GL2 of Z is the set of A is 2x2 matrix such that there exists B equals to A minus 1, and it belongs to also 2x2 integer matrix. But this is quite awkward definition. Well, the determinant of this inverse is, of course, the inverse of a determinant. And if this inverse is also an integer matrix, then of course it has integer determinant. Thus, we can see that if some matrix belongs to GL2Z or GLNZ, then its determinant is invertible in Z, so it is plus or minus 1.
Mm.
And so and we have proven this inclusion. Yes, that every matrix has a determinant plus or minus 1. But in fact, the converse is also true. because if you have you can you know the formula for inverse matrix in terms of this algebraic complement. You take some algebraic complement of a symmetric element, so you just so you know this formula with minors. So if you want to a minus 1 ij, then you need to consider a minor in our matrix that is obtained by removing not ij but gi element and its cross, so mgi, and then you divide it by the determinant of a. And this formula proves that if the determinant is plus or minus 1, then a to minus 1 is an integer matrix. Okay, but I need just this matrix 2, 1, 1, 1. Well, and I consider the following map. Let's let it. Well, let me. Let it be ft from the torus to itself, such that the point x maps to the point ax, where a is this matrix. Well, this is a map of the plane. So for any vector x maps to ax, just a linear map on that plane. But obviously, if 2 points are equivalent, if x equivalent to y, this means that x minus 1 belongs to z2. Then ax is also equivalent to ay, that is ax minus y belongs to z squared. Just because our matrix is integer. Moreover, since it's invertible, this map is also obviously invertible, and so the map T is invertible on a torus. So it is in fact, it is a diffeomorphism of a torus. I will try to draw it just a moment later. Well, okay, let's do this. Okay, so let's consider this point. Say this is a point. This is the origin. Then we can consider the fundamental domain of our torus, which is this this square. And let's draw its image. Well, the point 1, 0 maps to point 2 and 1. Oops, maps here. And point 0, 1 maps to this point. So and of course, the whole image is a parallelogram. Well, now it still is not clear how this image is again fit into torus. But of course, we want, if you want to consider the map on a torus as a map on this fundamental domain, on this square, you need to shift each segment. So there are 4 elements. You need to shift each of them into this square. So let me try to draw it in a bit larger. So we have this element. So this and this. This is A. Well, then we have this B. Then we have this C. And then you see we have just this D. So as we have already said, this is an homeomorphism or even diffeomorphism. And if you think about it as some map on a square, then you see that you need to have some manipulations. You need to cut something, you need to glue something, and so on. It's difficult to deal with this. But if you think on this map as a map on a torus, you have it's a nice continuous map. You don't need to glue or cut anything. So everything is quite nice. So this is a map. The name cat map was from one of the first figures that was discussed here. It was a figure of a cat. And so we have this image, and the next image is what is an image. So you can see that this cat is somehow stretched and sheared and so on. So it's quite complicated drawing, but it is possible to draw. And again, of course, if you look at this picture, you can see some fragments of cat. But in fact, these fragments are still, if you glue this rectangle, this square in a torus, then there is just a cat without any parts cut or glued in some weird manner. Just the same cat, but this stretched version. Okay, so this is a map. And I want to say that this map, okay, let me say that this is a theorem, that T, well, of course, it conserves the Lebesgue measure. Well, because if you have a linear map on a plane with a determinant +1 in this case, then it conserves the Lebesgue measure. This is just as the area. And of course, the same holds when you go to this spectrum. Okay, so we have this system, and this system is equivalent, is in fact isomorphic as a system of measured spaces to some map just that we have just discussed. So this is some Markov chain. We take some sequence, we forbid some sequences, and for other not forbidden words, we have transitional probabilities. We take some, we have the corresponding stationary distribution. So we have this Markov measure, which is shift invariant, and we have this. So in other words, how can we say this maybe a bit more explicitly? So we have this, and we have, well, let's say this, we have some H. Of course, this diagram should be commutative, and each arrow should preserve the corresponding measure. So, for example, H should maps the Lebesgue measure to, so pullback of Lebesgue measure under H should be mu. This is this is a theorem. And maybe I'll start this explanation today, and maybe I'll finish it next time because we have not too much time today. So the idea of the proof is the following. We want to construct so-called Markov coding. This is exactly this is more or less the same as I had just said. So I want to say that well, this H is not a bijection, but let's now not bother about these details. So I want to say that every point on a torus, I want to write it down as some sequence, as some Markov sequence, and then I want to show that if I make so that the sequences for the images are just the shifted sequences. Then if you for any point x, I consider some point some sequence omega n, and then since I want that for tx my sequence is just a shifted sequence, I can do this as follows. I can say, okay, I have x, and for this x, I somehow find omega naught. Then I can take, so this is some map. Or I can just say that I have a torus, and I split it into some parts, which are exactly our elements of our alphabet, our states of our Markov chain. I don't know now what is the set of the set of states, but suppose I do this. Then I want to do the following. That so omega naught of x is just the equals to j if and only if x belongs to aj. But then I can say from here that to find omega 1 of x, I just need to consider tx belongs to a j, or I want to say that this is x belongs to t minus 1 of aj, right? Because t is in bijection. And this is it. So, and in fact, I can continue this for any n. Yes. So I can look at this trivial equalities in two ways. First approach, you just take a point, and at the zero position of your sequence that you want to correspond to this, you so you write the number of aj such that you are now in for what you are now in. Then you go to tx and write down the number of the aj when you are placed now, and so on, forward, backward, and that's it. For a more another way is that you take this this decomposition of torus, this into this set, and then you take its pre-images. So it was one way to split torus into parts, which is aj's. Then you have t minus 1 of aj's, then t minus 2 of aj's, and so on. But so we have the same point, but the different. You look at the elements or at the number of elements in different decomposition of a torus. So that's it. Then, by definition, this thing is invariant. So this, by construction, this will hold. Because if you this is not a problem. Where is now a problem? The problem is that, first of all, we don't know whether this map is bijective or maybe, or at least close to bijective. And we don't know anything about the image. The image can be non-Markov, but some weird set. Why not? So we need some way to control this set. And to do this, we need to choose these AJs wisely, so that the intersections. So, by the way, you can also go backward here. So, for example, if you want to consider some point, assuming that everything is bijective, then this is an intersection over all n of t minus n of omega m. So if x corresponds to omega m of a omega m. So if these intersections, we can prove that these intersections are either empty if omega n is not allowed, or just one point, then everything is okay. Well, of course, we should also prove that Lebesgue measure corresponds to Markov measure and so on, but this is an idea. And now let me let me draw a figure how we will do this. Well, first of all, our metrics have two eigenvalues, two real eigenvalues. One of them is smaller than one, both positive, and one of them is larger than one. I'll write it as L lambda S, maybe, and lambda U. And there are corresponding eigenvectors, ES and EU. And you can see that, well, maybe I need a bit more, but let's start with this. Okay, so these vectors are situated as follows. Lambda 1 is here. This is EU, and ES is orthogonal because our matrix is symmetric. And I want to do the following. I want to split my torus now in two sets, which are rectangles with sides parallel to ES and EU. By the way, these directions ES and EU are irrational. This is quite easy to prove. You can just calculate it. So, for example, well, let's do it. 1, 1, 1 times EU, well, times some alpha 1 and alpha equals to, is proportional to 1 and alpha. Then you have 2 plus alpha is equal to 1 over alpha, which means that 2 alpha plus alpha square is this. And so you have this square, this equation of degree 2, and its roots are by 2. So if you take plus, so if you take minus, it is minus 1.612. And here it is 0.61. So it is somewhat like here. And this is orthogonal. Okay. And now, as I said, I want to draw these two rectangles, and I want to split a torus into two rectangles. Well, let's do this as follows. I'll first draw a picture, and then we'll discuss what is drawn here. Так. Так. Ну, вот, к сожалению, у меня сейчас немножко кривовато получается, но я думаю, что картинка уже становится понятной. Так, здесь у меня пропало. Вот такая картинка получается. Так. Вот такая получается картинка. Ну, видно, что здесь есть два, ну, в данном случае просто два квадрата, на самом деле. Но есть, в общем, короче говоря, вот этот вот квадратик поменьше, да. Есть, наоборот, не заштрихованный квадратик побольше. Значит, строгое доказательство того, что картинка такая, ну, там можно просто сказать, что вот мы проводим эти пересечения, ну, примерно до этого места, и поскольку мы знаем наклон, ну, там с какой-то точностью, но неважно, то мы понимаем, что все эти пересечения будут лежать вот именно так. Хорошо. Значит, вот разрезание нашей поверхности на два множества, на два набора квадратиков. Ну, или там прямоугольничков, даже сейчас не так важно. Давайте, кстати, поймем, сколько у нас на нашем торе мы сделали разрезов, чтобы разрезать тор на два вот этих прямоугольника. Оказывается, очень немного. А именно один разрез вот этот и один разрез вот этот. То есть я хочу сказать, что любая другая точка зеленая на этой картинке получается из вот этой красной буквы Т. Ну, значит, если красную букву Т сдвинуть на какой-то целочисленный вектор, то мы обязательно эту зеленую точку накроем. То есть здесь всего вот есть один отрезок направления EU. Значит, U и S это от слов stable и unstable, устойчивый и неустойчивый. Значит, вдоль неустойчивого мы от нуля убегаем, да, потому что там лямбда больше единицы, а вдоль устойчивого мы к нулю приближаемся, потому что там лямбда S меньше единицы. Так вот, что же произойдет? Да, давайте прежде чем поймем следующее. Значит, вот эта точка 0, она неподвижная. Ну, или, значит, на торе, это уж точно. Так, на плоскости мы можем 0, конечно, ставить в какую угодно точку. Давайте подумаем, что произойдет с этой картинкой, если мы теперь подействуем на нее нашим отображением. Что произойдет, в частности, вот с этой красной буквой Т? Ну, поскольку, как я уже сказал, у меня одно собственное значение, по-моему, меньше единицы, другое больше единицы, то у меня, собственно, вот эта шляпка буквы Т сожмется, а ножка буквы Т растянется. Но при этом я прошу заметить, то есть значит, произойдет вот что-то такое. То есть из нее получится, ну, вот что-то вот такое. Вот. Но при этом по-прежнему, если я возьму все ее сдвиги на соответственный вектор, то у меня вот эта пара отрезков, она по-прежнему будет разрезать тор на два прямоугольника. Эти два прямоугольника будут образами вот этих двух. Дальше надо заняться немножко занудным делом, все-таки нарисовать эти самые образы. Ну, давайте я попробую это сделать, а вы можете дома про это подумать, так сказать, нарисовав то же самое на клетчатой бумаге побольше и поровнее. Ну, смотрите, вот, например, давайте построим образы вот этого вот отрезка, вот этого вот квадратика. Вот этого. Значит, что мы можем сказать про его стороны? Ну, две стороны понятно. Это значит, они идут вдоль ЕУ и ЕС из нуля. Поэтому тут все понятно. А две другие у нас выходят из вот этих точек. Вот этой точки, из вот этой точки. Ну, идут там в соответствующих направлениях. Значит, для образов они будут идти из образов этих точек, ровно в тех же направлениях. Ну, давайте смотреть. Значит, точка минус 1, 0. Точка минус 1, 0 переводится нашим 2, 1, 1, 1 на минус 1, 0. Это что? Это точка минус 2, минус 1. Да? Да, у меня этой точки на картинке уже нет, но давайте попробуем ее туда пририсовать. Вот она на самом деле. Да, согласны? Значит, вот эта точка А, там какая-нибудь, не знаю, альфа, а вот это t в минус 1 от альфа. Точно так же, если я возьму вот эту вот точку бета, то это точка 0,1, и ее образ это точка 1,1. Вот она. T от бета. Простите, T от альфа здесь, конечно. Вот, поэтому, соответственно, картинка получается вот такая. Надо взять вот этот отрезок, его продлить. Ну и вот он будет. Значит, дальше тут, как вы видите, интересный вопрос. А вот эта вот линия, которую я сейчас рисую, она пройдет выше ТБ или ниже ТБ? Ну, значит, давайте поймем. У нас наклон этой прямой примерно 0,6, поэтому, значит, оно здесь дойдет до точки примерно 1,8. То есть оно выше, оно вот эту вертикальную прямую должно, вертикальная прямая x равно 2, оно пересечет где-то в точке 1,8. То есть она придет вот сюда. Так, вот у нас образ. Значит, вот он. Если мы нарисуем образ второго прямоугольника, ну давайте тоже это проделаем. Значит, что у нас здесь? Опять же, две стороны понятно какие. Вот, а две другие стороны, значит, одна выходит из вот этой точки, которая, значит, гамма, которая 0, минус 1. Значит, ее образ это минус 1, минус 1. Вот он. T от гамма. А другая точка, значит, это у нас вот эта точка. Дельта. Точка 1, 0, которая отображается в точку 2, 1. Вот сюда. Это дельта. Ну, давайте посмотрим теперь. Теперь я должен через дельту провести, естественно, такой же отрезок, а через гамму провести вот такой. Да? Значит, образ получается у меня вот он такой. И здесь уже, как мы знаем, это пройдет немножко выше, потому что оно пересекается прямо в точке 1 и 2. И получится вот такая картинка. Значит, здесь довольно трудно так на первый взгляд что-либо понять, но на самом деле, если на это... Сейчас, прошу прощения, что-то мне это не нравится. Нет, пардон, конечно, все не так. Смотрите, вот верхняя сторона, вот она, вот она. Сейчас нет, даже что-то я не то нарисовал. Значит, две стороны. Значит, вот эта сторона, понятно, вот она. Дальше я иду здесь, а дальше я иду вот здесь. Во. Вот теперь все правильно. Значит, итого, давайте я теперь попробую из этой картинки извлечь какие-то уже геометрические выводы. И чтобы было рисовать удобнее, я нарисую все то же самое, но повернув это вот так. Да, вот у меня было два прямоугольника. Давайте их назовем R1 и R2. Если я посмотрю на образ, ну, например, на образ R1, то этот образ R1, он что сделает? Он, во-первых, вот здесь отрежет некоторую полосочку, а во-вторых, вот здесь отрежет такую полосочку. Значит, вот это вот все, это TR1. Логичным образом TR2 нам что даст? Смотрите, он сначала даст нам кусок вот этот, примыкающий к нулю. Потом это будет кусок вот этот вот, который вот этот. И потом это будет снова вот эта полосочка. Значит, вот это TR2. Можно нарисовать еще, так сказать, картинку в чем-то симметричную. Можно нарисовать два длинных отрезочка, два длинных прямоугольничка. И посмотреть теперь наоборот. Вот у меня есть этот длинный прямоугольник, и я могу посмотреть, что начало его – это кусок R1, а потом кусок R2. И наоборот, если я посмотрю на синий, то он будет вот такой. Здесь будет R2, здесь будет R1, а здесь будет снова R2. Ну, не очень получилось в масштабе, давайте. Вот как-то так. Вот она, картинка. На самом деле, значит, здесь сделано уже почти все. Отсюда до настоящего марковского кодирования остался один шаг. Как, ну, казалось бы, что тут делать? Значит, мы берем элемент, ну, берем какую-нибудь последовательность. Судя по тому, что у нас все совсем пересекается, можем брать вообще любую последовательность из ноликов и единичек, ну, из единичек и двоек, точнее. Дальше мы должны рассматривать вот такие вот пересечения, как нам здесь указано. Вот такой вот. Ну и надеяться, что если мы все сделали правильно и нам повезет, что это пересечение будет стоять из одной точки. Ну и тогда, значит, все заработает. Вот оно, марковское кодирование. Но если немножко повозиться с этими картинками, то будет видно, что пересечение не будет состоять из одной точки. Не будет оно состоять из одной точки примерно по следующей причине. Вот смотрите, что я вижу на этой картинке. Что если я возьму отрезок множества R2 и рассмотрю образ R2, то образ R2 пересечет TR2 два раза. А если я, например, захочу нарисовать второй образ, вот если я теперь захочу нарисовать, давайте скажем, так, обозначить t в квадрате от R2. Как мне это сделать? Конечно, я могу снова рисовать вот эти жуткие картинки там, с образами точек, но понятно, что там надо будет уже уходить куда-то значительно дальше. К счастью, ничего этого делать не надо. Вот смотрите. Вот у меня здесь нарисован вот этот вот фиолетовый отрезок t от R2. Я знаю, вот смотрите, то есть можно теперь посмотреть на эту на верхнюю картинку и взять, просто применить к ней t, ну, то есть сжать и растянуть. При этом, естественно, скажем, R2 здесь перейдет вот в TR2 здесь. А, соответственно, то, что раньше было изображением TR2, станет отображением T квадрат R2. Что же у меня получится? Получится у меня следующее, что это самый T квадрат от R2. Это будет, он 2 раза пересечет, то есть это будет вот, он, ну как мы договорились, он 2 раза пересекает вот это, ниже, так сказать, большой T от R2, и 1 раз вот здесь сверху пересекает маленький. Согласны? Значит, эта картинка просто получается, потому что вот между этими картинками есть отображение T. И значит, если на верхней картинке T от R2 вот такое вот высекал в R1 и в R2, то, соответственно, его образ T квадрат от R2 будет высекать вот такое в TR1 и в TR2. Вот что и нарисовано. А теперь мы сделаем объединение этих двух картинок. Мы ведь знаем, что TR2 – это вот такая полосочка, в которой, значит, ну вот какую-то верхнюю часть занимает, ну точнее, там есть даже целых 2 полосочки, образ T квадрат от R2. То есть T квадрат от R2, вот смотрите, как он будет выглядеть. Он будет выглядеть вот так. Сейчас. Я боюсь, что уже ничего не осталось, не стало видно, но смотрите, что здесь сделано. Я от каждой полосочки отрезал, ну, вот какие-то там верхние, условно, 2/3. И вот это будет, вот то, что здесь нарисовано, это t квадрат от R2. Ну, потому что просто из нижнего рисунка мы видели, что в фиолетовой вот этой полоске, вот в этой фиолетовой полоске, вот эта наша красная составляет верхние, там, ну, условно говоря, 2/3. Поэтому картинка будет вот такая. Ну, теперь давайте, например, посмотрим на пересечение R2, TR2, T квадрат R2. Оно состоит из двух прямоугольничков. Ну, вот из вот этого и из вот этого. Если мы будем дальше к нему чего-то пририсовывать, еще там добавлять пересечение с каким-нибудь R3 или наоборот пересечение с каким-то прошлым, то я, давайте так скажу на пальцах, что с каждой из этих полосочек от нее будут по-прежнему отрезаться какие-то куски. Ну, например, если мы будем довешивать что-то назад, то будут вырезаться вертикальные полоски. Вот если я, например, зафиксирую там еще какой-нибудь, что там, на предыдущем шаге лежал, скажем, в R1, то есть сюда допишу T-1 от R, там, скажем, 1, то я вырежу вот такое. И у меня останется, соответственно, вот 2 таких множества. И так далее. А если я вперед буду приписывать, то я из каждой полосочки буду что-то вырезать. Поэтому уже видно, что вот эти 2 полосочки, каждая из них мне в пересечении даст по точке. А если у меня по дороге еще там появятся какие-то такие штуки, что еще там все это как-то измельчится, то точек будет там не 2, а 4, 8, ну сколько надо. Короче говоря, получается, что это кодирование, оно недостаточно. То есть просто информация о том, в каких отрезках R1 и R2 я лежал на каждом из шагов, ее недостаточно для того, чтобы однозначно закодировать точку. Оказывается, и в следующий раз мы, я думаю, это сделаем, это такое симпатичное упражнение, достаточно следующего. Давайте я на этой картинке попробую сейчас убрать все лишнее, чтобы так, понятно. Сейчас ничего не останется. Попробую нарисовать все-таки, что я имею в виду. я сделаю вот что. Я возьму вот эти 5 отрезков, 5 прямоугольничков и их и обозначу А1, А2, А3, А4 и А5. И вот утверждение, что вот это вот разбиение, это и будет наше задает марковское кодирование. Более или менее надо проверить, что вот здесь уже никаких таких хитростей нет. Здесь два отрезка, либо там, ну, два прямоугольничка, они либо там пересекаются по чему-то, опять же, одному прямоугольничку, либо просто совпадают, либо просто не пересекаются. Точнее, там есть некоторое, так сказать, техническое уточнение, связанное с тем, что прямоугольники там, как бы они геометрически не пересекаются, а какими-нибудь там граничными точками могут пересечься. Поэтому вот ту формулу, которую я писал, вот эту формулу, ее надо на самом деле будет уточнить. Правильная формула, ну давайте я уж это напишу и, может быть, на этом и закончу. Давай, можно так написать, что я беру я пересекаю внутренности сейчас только я здесь, да, t минус n. Я пересекаю внутренности, ну, в конечном числе, а потом замыкаю, а потом перехожу, собственно, к пределу, ну, к пересечению, точнее. И вот тогда, оказывается, получается все совсем правильно, потому что вот эти, так сказать, паразитные там пересечения какими-то концами, они, участками границы, они здесь нам ничего не портят. Вот, значит, вот такая конструкция. В следующий раз мы ее, я надеюсь, закончим. Но, значит, что я хочу здесь как бы подчеркнуть, что эта конструкция, она, конечно, вот для одного очень специального отображения, и для него мы показали, что, значит, что наша, что оно с мерой Лебега, оно, в общем-то, ну, практически такое же, как некоторая марковская цепь. И, соответственно, дальше можно, скажем, переводить какие-то утверждения на язык этих самых марковских цепей. Ну, как, ну, одно отображение, ну, прекрасно. А как бы, мало ли это, что там можно для одного отображения сделать. Но оказывается, что вот эта конструкция, ну и вообще много чего вокруг этого, она обладает таким удивительным свойством, что если вы возьмете отображение и немножко его пошевелите, ну, то есть добавите к вот этому нашему 2,1,1,1 какую-нибудь нелинейную добавку, ну, не очень большую, там, по какой-нибудь, там, не знаю, C1 норме или там даже C2, C3, ну, в общем, что-то, так сказать, расширить, то тогда у вас получится отображение, которое ведет себя в сущности так же. И поэтому оно тоже будет сопряжено вот всему этому и так далее. Но, правда, у него уже инвариантная мера, может быть, не мера Лебега, а стоит другая. Вот, поэтому, с одной стороны, здесь от возмущения ничего не зависит, а с другой стороны, кое-что все-таки меняется, инвариантная мера при этом может стать достаточно гадкой. Вот. Ну, вот на этом я сегодня остановлюсь, а в двух оставшихся занятиях мы как раз постараемся более подробно обсудить вот эту связь между гладкой системой и чем-то вот таким, так сказать, вероятностным. Вот. Ну, если вопросов нет, то давайте на этом закончим.
Хорошо, спасибо. Я только в последней конструкции запутался немного.
Я ее, так сказать, в какой-то мере повторю в следующий раз, ну, потому что я ее в любом случае не закончил. Но давай, смотрите, значит, что нужно, значит, попробовать, значит, во-первых, поняли ли вы вот эти картинки, значит, почему у нас вот эти рисунки, где, значит, что здесь нарисовано? Здесь нарисовано, как соотносятся образы и прообразы, да, значит, как соотносятся R1 и R2, а также TR1 и TR2. И эти две картинки, они, значит, показывают, как эти два набора прямоугольников, так сказать, если вот я один нарисую как целиковый прямоугольник, как в нем лежат другие, ну, как, вернее, как они его пересекают. Можете попробовать нарисовать теперь такую же картинку для 5, вот, которые здесь написаны. То есть надо нарисовать картинку, которая покажет, как вот она будет, то есть у нее, ну, скажем, это как и здесь будет 2 картинки, ну, вот можно одну нарисовать, да, вот одну вот такую. Вот вам ваши 5 прямоугольников. А1, А2, А3, А4, 4, А5. А дальше вы берете, задаете таким вопросом, а где на этой картинке, например, TA1? Ну, он будет тоже какой-то такой полосочкой, и можно эту полосочку нарисовать. Потом нарисовать TA2 и так далее. Это можно делать по-прежнему, значит, рисуя вот, так сказать, вот на этой картинке. А можно получать это вот из этих 2 картинок, которые уже есть. Ну, потому что, вот как я объяснил, для второго образа тут все, в общем-то, нарисовано было. Ну, было нарисовано красным, пока я не стер. Вот, собственно, и все. И вот эта картинка, с нее я, собственно, в следующий раз и начну. Она нам и позволит построить уже наше итоговое марковское разбиение. Вот. Но тут, в общем, такое место, где, может быть, полезно немножко самому руками поработать, чтобы было понятно, что из чего следует. Вот. Ладно, я это в следующий раз в любом случае расскажу. Запрос я понял. Но на сегодня давайте тогда закончим.